Hello, my name is Rodrigo Canaan, and I'm going to talk about my paper, Behavioral Evaluation of Hanabi Rainbow GQN Agents and Role-Based Agents. You can see my co-authors on the screen, and a QR code for the paper and GitHub if you're interested. The main question that motivates this paper is, how well do existing reinforcement learning agents in Hanabi adapt to partners that were not seen during training? And to see why this is interesting, let's talk a bit about Hanabi. Hanabi is a cooperative card game for 2 to 5 players that is a great testbed for cooperative AI that models other players or uses theory of mind. In Hanabi, the objective of the game is to build color piles of cards by playing cards of each color in ascending order of value. However, what makes the game unique is that players do not see their own hands. Instead, they play with their hands facing outwards. The only way to get information about the colors and values of your card is through a system of hints, which is the only method of communication allowed in the game. And because these hints are restricted, players will often act on incomplete information and must do their best to figure out, for example, which cards in their hands are immediately playable and which should be saved for later. In each player's turn, they pick between 3 actions: playing a card, giving a hint, which consumes a token from a shared pool, and discarding a card, which recovers the token. They alternate turns until either the deck runs out, or the team runs out of lives, or all piles are complete. As an example, let's say it's my turn and the board is as seen on the right. I could use a hint token to tell my partner that this card is yellow, in the hopes that they play it. But remember that their perspective looks like this. At this point, they do not know the card's value, only its color. If this was anything but a yellow 4 and they attempted to play it, it would be a mistake and the group would lose a life. But if I'm playing with a human partner, they're likely to put themselves in my position and realize that the only reason I'm giving a hint about yellow is because it is the 4. In practice, there's an implicit convention in place that says players should prioritize hints about playable cards. If they do decide to play the card, they would reveal it, see that it fits the board, and we would score a point, and they would draw a replacement card. But if I were not following this convention and giving hints at random, this might have been a very bad move. Now, if it were my turn again, I might want to try to get them to play their new green 2. But note that telling them just about this 2 would be illegal, as they have another 2 in hand and the rules required me to give full information. If I wanted, I could point at both 2s, but only one of them would be playable. They might reason that the recently drawn 2 is more relevant, effectively adding another layer of convention and player modeling. With more and more assumptions, even more efficient plays are possible, but this can get very complex and generalize poorly to agents that are not playing by the same conventions. And the interesting thing is that current state-of-the-art reinforcement learning agents for the game can learn some very complex and arbitrary conventions via self-play and do extremely well with them. Of course, this is good for self-play, but bad for more general scenarios where we're interested in playing with unknown agents or even with humans. But what if instead of self-play, we train them by pairing them with simpler partners? So in this paper, we study a specific reinforcement learning agent called Rainbow and how it performs when we select training partners from a pool of simpler rule-based agents and evaluate based on the performance on the entire unseen pool. Some training partners lead to more general training policies than others, so we also perform a behavioral analysis to shed light on why this might be the case. Let me start by describing these simpler agents we use as partners. They are called rule-based agents because, as you can see, they play by following rules in a certain order. Each rule has a condition which, if applicable, results in an action. Otherwise, the agent moves to the next. Most of these rules describe simple heuristics for when to play, discard, or hint a card. And different combinations of these rules or reorderings of the rules will give rise to different agents. So Internal is one example of rule-based agent, but in this paper we focus on 6 such agents that are part of the early Hanabi literature, and they were compiled in a 2017 paper by Walton Rivers and distributed in Java as part of their Hanabi competition framework. For this paper, we re-implement them in the Hanabi learning environment, which is another framework I'll introduce in a minute. In the top of the screen, you can see the self-play score of each agent in the 2-player version of the game and a reference to their original papers. In the bottom, you see their scores when playing with each other. With the exception of Flawed, which was designed to be tricky to play with on purpose, They score from 10 to 17 points on average, and their strategies seem broadly compatible based on the scores they achieve when paired with one another. This broad compatibility of strategies quickly vanishes, though, when we look instead at state-of-the-art reinforcement learning agents. Here we can see 4 of them. In comments in the original papers, the authors of 3 of them noted that they learned conventions that map arbitrary colors to arbitrary actions. This leads them to perform poorly even among independently trained instances of the same architecture. Rainbow, on the other hand, was noted by its authors to converge each time to similar strategies, and it seems to not learn these types of undesired conventions. This is why we picked Rainbow for this paper. The Hanabi Rainbow agent was included as a sample agent in the Hanabi learning environment, a Python framework described in a paper by Bard et al. It is trained using a modification of the DQN algorithm. This is the version we use in our experiments, with the same hyperparameters, changing only the choice of training partners. The agent itself uses a simple feed-forward neural network to estimate value distributions for each action. The input space includes only one turn of game history, but provides features representing the information currently known to each agent. Since this agent has limited memory and no direct modeling of the other player, we did not expect it to learn to identify or adapt to its partners. Rather, we knew it seemed to avoid some problematic conventions, so there was a chance its policy might be broadly compatible with the ones used by the rule-based agent. So what we did is we took each rule-based agent and we trained a few instances of Rainbow using that specific agent as a partner. We also trained a few instances of Rainbow purely via self-play, and we trained a few instances that sampled evenly from all 6 rule-based agents during training. Optionally, some versions could also include self-play in this mix. But what we're interested on is what happens when we take these agents trained with some partners and put them to play with the unseen ones in the pool. We are also interested in their own self-play behaviors. So if we do this for every possible matchup, we get something like this, where the dotted lines represent training partners and the red lines represent matchups playing during evaluation. You can see the results on this table. Here in the left column, we represent the Rainbow agents that trained with a single partner in blue, the ones that were trained in self-play in yellow, and the ones that were trained with all the rule-based partners, with or without self-play, in red. All the scores are the average of each matchup over 4 independently trained instances of the corresponding Rainbow agent in the 2-player version of the game. As you can see in the main diagonal, the agents that trained with a single partner scored the highest with that partner. They also score higher than that partner's self-play. So for example, where Pierce has a self-play score of 16.6, Rainbow Pierce scores 17.6 in that matchup. The self-play agents score pretty well in self-play, as should be expected, but they perform very poorly with the remaining partners. Apparently, the learned strategy wasn't very general after all. In all fairness, the agents that trained with one of the rule-based partners do not fare well in self-play either, with the exception of Rainbow Internal. Interestingly, Rainbow AIIDE had one of the highest scores with its intended partner, but the lowest self-play and aggregate score. And finally, the Rainbow Internal achieved some surprisingly high self-play and aggregate score. Something about Internal seems to make Rainbow learn a robust general policy when trained with it. So, what makes agents trained with some partners learn more general policies than agents trained with others? To start addressing these questions, we look for some metrics that help characterize how an agent plays rather than just how well it scores. We started with metrics developed in one of our previous papers. Communicativeness measures how often the agent chooses a hint action, given that at least one hint token is available, and information per play measures how many pieces of information, that is, color and value, the agent knows on average at the time of playing a card. We also looked into how many correct plays and mistakes each agent makes in each of its matchups. This helps us discern whether an agent is doing poorly because it can't understand its partner's hint, or if it can't give hints that its partners understand. Games bombed out refers to games where 3 lives are lost due to mistakes. In these games, the team scores 0, regardless of how many cards were successfully played. All these metrics were collected for all the matchups and aggregated in this table. While there is a lot of information to digest, let me guide you through some of the most interesting findings. Rainbow Self-Play has an information per play of almost exactly 1. This is the lowest of any rainbow agent, and seems to imply it learns some sort of very optimized one hint, one play convention. But this does not translate to many correct plays with the remaining partners at around 4.3, and it is unable to give hints that other players understand at only 3.7. Rainbow Internal and Rainbow AIIDE show an interesting contrast. Rainbow Internal makes plenty of mistakes with its intended partner, but few mistakes in aggregate. Rainbow AIIDE is the reverse, making among the fewest mistakes with its intended partner, but the highest number of mistakes in aggregate. In fact, Rainbow AIIDE managed to bomb out almost 70% of its games across all matchups. In the paper, we speculate that this might be linked to the fact that AIIDE gives hints in a very predictable way about playable cards, while Internal will sometimes give random hints. To summarize these results, we found that training with a single partner, including self-play, usually generalizes poorly, with one important exception. And the type of behavioral analysis we perform helps raise hypotheses for identifying good partners for policy generality. In terms of future work, none of the agents discussed are trying to identify or adapt to its partners, so exploring mechanisms to do that would be interesting. This could perhaps be achieved by an explicit mechanism or simply through different neural network architectures, especially recurrent ones. We would also like to further investigate the impact of partner selection into policy generality and investigate the relationship between performance with one or more partners and performance with humans. To conclude, here are the links to the paper and the code, as well as some references I mentioned during this talk. As a disclaimer, an earlier version of this work was presented at a AAAI workshop earlier this year, and some values in this presentation may be different than the paper due to a correction of a small error involving the information properly metric. Thank you for listening.